Hello, thanks for clicking on another pre-Narculus production. Today we're going to talk about Newton's law of cooling. It's Newton's favorite law of cooling. Okay, this is an exciting law that all of you can see the practical applications of and what it might be used for. All right, so let's get started and we'll talk about it and we'll try some examples. Here we go. Okay, so Newton's law of cooling fancily says that the temperature of a heated object decreases exponentially over time toward the temperature of the surrounding medium. Okay? In simple terms, if you take a cake, right, you put it in the oven to bake at 350 degrees. Okay? When you take the cake out and put it on the counter, the temperature of the cake it goes down, right? It cools, okay? The temperature, it cools off. Now, how low does the temperature go? Well, the temperature certainly doesn't go to like 0 unless the temperature of your house is 0, right? It cools down to the temperature of the room, right? Whatever the temperature is in the kitchen, that's what temperature the cake will end up at. That's what Newton's law of cooling says, okay? That's simply what it says. All right. Now, Newton's law of cooling is it looks extremely complicated. This is the law. U of t equals big T plus U naught minus big T e to the k little t. Okay. There's a lot of letters floating around here, but a lot of these we have some familiarity with. So we'll write over here, U of t is the temperature after time. After some time passes, U of t will be the temperature. Big T is the temperature of the surroundings. Okay, so temperature of the surroundings, what I mean by that is if you take the cake out of the oven and put it on the counter, right, whatever the temperature is in your kitchen, that's the temperature of the cake's surroundings. Okay, if you take a soda bottle and put it into the refrigerator, right, the temperature of the surroundings is the temperature of the refrigerator. That's what you put it in. Okay, that's temperature of the surroundings, big T. All right, U sub 0, U naught, is the initial temperature. So in our cake example, our initial temperature would be 350. You take it out of the oven, it's at 350. Okay, K is the constant of proportionality. All right, that's usually what you have to find first. Okay, find first before you can usually do anything else. And then little t is time. The time can be in any unit as long as it's consistent across the board. So if you start in hours, then you have to keep going. All your values have to be in hours. Okay? That's what all of these variables all stand for. All right? And you're going to be finding K first, and we're going to go from there. Okay, so let's try an example here. So a pot of coffee with temperature 100 degrees Celsius is set down in a room, okay, with a temperature of 20 degrees. The coffee cools to 60 degrees Celsius after 1 hour. Letter A says find the values of T, U naught, and K. All right, so our equation is going to be U of T equals big T plus U naught minus big T e to the KT power. Our goal is to find K first. All right, but before we do that, let's put down all our little variables here. Okay, we have U of T, we have big T, we have U naught, we have K, and we have little t. All these things are variables, so all of them should get values or a question mark. So the pot of coffee with a temperature of 100 degrees Celsius is set down in the room. So that means the 100 degrees is the initial temperature, okay, when it comes off the stove. The room temperature is 20 degrees. So big T is 20. Okay, the coffee cools to 60 degrees Celsius. That's the temperature after 1 hour's time. And that leaves me with find K. Okay? All right, so let's take all these numbers, plug them in. So we have 60 equals 20 plus 100 minus 20 e to the k times 1. All right, so now let's clean this up a little bit. This isn't much more complicated to solve than anything else we've solved for so far, although it looks kind of fancy. Okay, so we want to solve for k. K is up in the exponent. So we're going to have to move a lot of stuff first. Let's subtract the 20, get it out of there. Now let's divide by 80 to get that out of there. So 40 over 80 is a half. So we have 1/2 equals e to the k. Now we want to solve for k. K is up in the exponent. I'm going to have to take the natural log on both sides to get the power down. So I have k ln e. That's an n. All right. So k ln e, natural log of e, that's a 1. So there's k. K is ln 1/2. Okay, now this number we're going to have to remember as we go on. All right, we're going to need that to keep going in the rest of the part. So we found k, that's important. All right, so let's take that and move ahead. Let's see where we can go to next. We know k is ln 1/2. Now, find the temperature of coffee after half an hour. So here's my equation. U of t equals big T plus U naught minus big T e to the k little t. All right, so we have UT, we have big T, U naught, K, and little t. K is ln 1/2. Okay. We still have the numbers from the previous page. Find the temperature of the coffee after half an hour. Half an hour means T is going to be 1/2, right? Because on the previous page, we used 1 hour for little t. So our units have to be consistent. So we just used hours in part A. We got to use hours in part B. So it's going to be half an hour. U naught is, what was it? It was 100, right? That was the initial temperature of the coffee. Big T is 20. And U of t is what we want. Now, what's my temperature after? So U of t, so U of 1/2, is going to equal 20 plus 100 minus 20 e to the ln 1/2 times 1/2. Now, the only tricky part here is that you cannot multiply this half and this half because one's in a natural log and one is not. So I just have to write everything that's there. And actually, I could literally take everything that's here and type the whole thing into the calculator as long as you're careful with your parentheses. You do it in one shot, and you'll get U of 1/2 comes out to be 76.5685 degrees. So that's the temperature of the coffee after half an hour. And that should make sense. I mean, your answer you get should make sense. You can kind of have an idea, kind of check it. It started at 100. You know it's going down to 20 degrees. After a half an hour, well, that's good. The temperature dropped from 100, right? I mean, if you're getting an answer that's 135 and the temperature is supposed to drop, well, how's that possible? It started at 100. How's it going up? It makes no sense. Okay, so you can kind of, at least check, I guess, common sense wise. All right, let's go to part C. How long did it take the coffee to cool to reach 50 degrees? How long? So now I want to know little t. So the temperature after has to be 50. The room temperature is still 20. Okay. The initial temperature is still 100. K is still ln 1/2. And little t is what I want to know. All right, so let's take everything and plug it in. U of t equals big T plus U naught minus big T e to the k little t. We have 50 equals 20 plus 100 minus 20 e to the t times ln 1/2. I just wrote that in the opposite order. All right, so let's clean this up here. We have 50 equals 20 plus 80 e to the t ln 1/2. We're trying to solve for t. So let's subtract 20. We have 30 equals 80 e to the t ln 1/2. Divide by 80. So that gives us 3/8 equals e to the t ln 1/2. Let's take the natural log on both sides to get the power down. So ln 3/8 will equal t ln 1/2 times ln e, right? This whole thing was the power, and then I took the ln and put it in front of the e. ln e is a 1, so I don't need it. So now I'm going to divide both sides by ln 1/2 to get t alone. So in your calculator, you're going to do ln 3/8, close the parentheses, and then divide by ln 1/2, close the parentheses, and you'll come out with t is 1.415 hours. Okay, we started our unit in hours. That means our answers for t will come out in hours. So there is your correct answer. All right, that's how you would go about doing Newton's law of cooling. Okay, so we're going to try one more. So it's a little different. You maybe never done this before. A cheesecake is taken out of the oven with an ideal internal temperature of 165 degrees Fahrenheit and placed into a 35 degree Fahrenheit refrigerator. Okay, after 10 minutes, the cheesecake has cooled to 150. If we must wait until the cheesecake has cooled to 70 degrees before we eat it, how long will we have to wait? All right, so the first thing we have to do is find K. Okay, we don't know K. But we should have enough information to get K. So U of T equals big T plus U naught minus big T, e to the K level T. All right, so we got U of T, we have big T, we have U naught, K, and little t. All right, so the temperature after 10 minutes, the temperature was 150. So after 10 minutes, the temperature was 150. Big T is it's going into the refrigerator, 35 degrees. The initial temperature was 165, and that's enough to get K. All right, so we have 150 equals 35 plus 165 minus 35 e to the 10K. Okay, so I'm going to subtract the 35 here on both sides, and then in the meantime, I'll do the parentheses. So now I have 115 equals 130 e to the 10K. Divide by 130 on both sides. We have 115 over 130 equals e to the 10K. Take the natural log on both sides to get the power down. So now we'll have the natural log of 115 over 130 equals 10K ln e, but ln e is a 1. We don't need it. And we're going to divide both sides by 10. Sorry, I'm running short on room here. And we're going to get K. We'll stick it up here. K is ln 115 over 130. That whole thing divided by 10. All right, so let's put that over here. We now know what K is. ln 115 over 130, all divided by 10. All right, now let's reset our numbers here, because now we want to answer the question that they asked, now that we have K. All right, so now it says, if we must wait until the cheesecake is cooled to 70 degrees, so after the temperature has to be 70, how long do we have to wait to eat it? So the question mark is how long. The temperature, the room temperature, well, the temperature of the fridge is 35, and the initial temperature was 165. Okay, all right, so now let's come over here, and we're going to have, let's see, I might be able to fit it. All right, we're going to have 70 equals 35 plus 165 minus 35 e to the ln 115 over 130 all over 10 times t. All that's in the exponent. All right, let me see if I can move over here. I'm going to move the 35 by subtracting it. Let me subtract 35 on both sides, and I'll move everything over. So we have 35 is equal to 130 e to the t times ln 115 over 130 all over 10. That's in the exponent. All right, let's divide both sides by 130. Okay. And now we're going to have 35 over 130 equals e to the t ln 115 over 130 all divided by 10. All right, now we got to take the ln on both sides. I'm out of room, so I'm going to have to go back and erase some of this that I already did. Do that real quick. Okay. Isn't this exciting? Bet you don't see Khan ever erase stuff, right? That's why you show up here to pre-narculus. All right, so let's take the ln on both sides. ln 35 over 130 equals t times ln 115 over 130 all over 10 times ln e, but ln e is 1. I don't need it. All right, so now I'm going to multiply both sides by the reciprocal of this. So I have t is equal to 10 ln 35 over 130 divided by ln 115 over 130. Okay, so t comes out to be 106.6818 minutes. Okay, I started in minutes, right? 10 minutes. That's what I used to find k. So my answer is in minutes. Okay. Now, please note that k is equal to approximately negative 0.0123. So if that's easier for you, you could take this value of k, convert it to a decimal, and then use that value, that decimal, okay, to finish out your rest of your calculation if that's a little easier for you. But I actually would go further than this. This is 4 decimal places. I would actually go out to like 6 or 7. You want to make sure you get the correct answer up to a certain number of decimal places to be considered having a correct answer. All right? And that's it for Newton's law. Thanks for clicking.